Welcome to Solidity Fridays, where a bunch of us smooth-brained Solidity hang out with people who actually know what they're doing and read some Solidity code together. This week we are joined by Odysseas and Anna from the NOMAD team. NOMAD, as you can see, is the future of cross-chain, a bridge that is being built multi-chain across a number of different L1s, and actually, I don't know, maybe even L2s too. I guess we'll dive into that. Yeah, welcome. So a lot of times we start off kind of before we look at code, just kind of asking about how you guys got into Web3, maybe some general questions about bridges also. So Anna, Odysseus, if either of you want to start, I guess, about who you are, what you do at NOMAD, and I guess how you ended up there, that would be great.
Yeah, I can give a
Anna.
start. My name's Anna. I'm the protocol lead at NOMAD. I got into Web3 quite a while back. At the time, I was working on a lot of tech for social impact projects, and that's when I kind of first heard about crypto and kind of fell in love. Have been pretty obsessed with the space ever since then. Started working on NOMAD when I met James Prestwich in January of 2021. It was a couple weeks after he had just had the idea for this concept, and we've been working on the protocol together since then. And that's what's bloomed into kind of the team and the company building NOMAD.
Cool.
Hello, I'm a protocol engineer. I'm Odysseas. Quite funnily, I started doing blockchain in 2017, but I ended up in all the wrong projects, and I was really upset and left the industry for good. And like after 3 years, last August, I read again the Sovereign Individual, the book, for those who know. And it really struck me that blockchain is the future in a lot of industries and a lot of how the world is changing. And I got really hooked up, and ever since I've been trying to dive deeper into. I was very lucky to meet the Nomad team in Denver, and now I'm here.
This time you ended up in the right places, it sounds like.
Oh yeah.
Cool.
Now he's about
So,
a couple weeks away from leaving the industry for good again.
hope not. Uh, uh, yeah. Truth is, Odysseus, we've had you around by Solidity Fridays for a while. I think you were kind of one of the early adopters over here. So, I mean, big thanks from our end for that also. So NOMAD is a multi-chain bridge. So just, I guess, like the general questions first. Um, Something that blockchains are really bad at in general is kind of knowing what happens outside of a blockchain or outside its own blockchain. We have entire entities like Chainlink that basically are trying to get information to a blockchain from outside. We see all kinds of Oracle attacks, things like that. So when you're making a bridge and you're moving things from one chain to another, what are the general ways to make blockchain B know that something already happened on blockchain A?
Yeah. So we can sort of break this down into a couple of broad chunks. The first thing I would note is sort of internally verified systems. That would be like header relays, full header relays, which basically perform the consensus rules of another chain inside of the VM of the receiving chain. And these are very heavyweight to implement, but they are the highest, kind of most perfect gold standard for security. Um, on the other end of the spectrum, we have sort of proof of authority constructions. These are things like multi-sigs or validator bridges. And these are situations in which an external party, be it a multi-sig signer or a validator with a stake that gets rotated, attests to what has happened outside of the chain. Um, and that was really broadly the state of the world before NOMAD came along, or this team came along and started working on bridges. NOMAD is the third category now of bridges, and we are optimistically verified. So basically a construction similar to optimistic rollups, wherein a single party attests to changes on a sending chain, and a group of parties watch those attestations and block them if they're fraudulent.
So basically, you've got validators looking at things, so they have the ability to, like, that's what they're verifying against. And then, so like this kind of validator set, being that there is a valid, oh, actually, wait, so it wouldn't need to be a validator set. It's really anyone could just observe what's happening on chain A and challenge anything that's fraudulently proposed on chain B. Is that it?
That's exactly right. So, Odiko.
Yeah, I think a useful mental model to think is that the usual proof of authority validator systems are, you have a system that decides for you who to trust, right? You trust a multisig, whether that multisig is a constant multisig, it changes based on some rules, whatever, but it's a system-wide multisig. Whether in our system you decide who to trust, because you don't trust the validators. Basically, you trust the watcher that watches over your application and make sure that no fraud is happening, right? So it's not a matter of you you minimize trust, but allowing you to choose who to trust.
Mhm. And theoretically,
also a
anybody could be a watcher. Is that sorry? Cut you off.
Oh, no worries, no worries. Actually, Odie did some good, made an awesome diagram about this. Odie, you want to take this?
Sorry, for diagram for what? Sorry, I
Oh, watcher
missed this.
permissions, basically, basically the
Yeah.
answer here is that this is different on the sending chain as it is on the receiving chain.
Mhm. So it is actually like a specific role. It's not just that anybody can be watching the chain and make a challenge. It's like, so you specifically have to do something to be a watcher.
So so on the sending chain, absolutely anybody can be a watcher, anybody can observe fraud and slash the updater if they are fraudulent. So it's basically like very strong guarantee that if the updater has any like shenanigans, they will be slashed on the home chain. Anyone can do that. And then on the receiving chain, the watcher is a permissioned role. The reason for this is that there is no way to like uh, uh, like verify 100% that the watcher is necessarily like you cannot prove fraud on the receiving chain. That's kind of by nature of the system, because what we're trying to do is get information from one chain to another. In order to prove fraud, you have to have the perfect information on the sending chain. So what we've done with the watcher role on the receiving chain is we've attempted to minimize and localize the trust of that role. So two major things. First, applications choose their watcher set. This is not a system-wide role. Applications are essentially sovereign in who they trust to play this role. And the second thing is that in our system, trust is significantly minimized relevant to like a validator or a multi-sig bridge. In a validator or a multi-sig bridge, the parties that you trust are trusted to tell you what happened. They get to submit transactions on your behalf, essentially. And also in those systems, there is no time lock. So if they submit a kind of false or wrong transaction, then it's basically game over. And that's the trust that you're placing in them. Um, in our system, the trust that's placed in watchers on the receiving chain is to block or to revoke permission if there's something wrong. So they cannot cause safety failures. They cannot submit fraudulent transactions themselves. All they can do is pause the channel.
Cool. Actually, yeah, Ben, do you mind sharing that diagram that Odysseus just put in the chat? Ah, cool. Here we are.
Yeah, sure.
So, Maybe if you could just help me out a little bit with what we're looking at here. So it looks like we've got the Halt replica and the Halt home. It's kind of like the originating chain and the destination chain.
That's right.
Yes, right. So anyone can prove. That's why it's permissionless and home, because the chain can verify itself on the validity of the proof. But on the receiving chain, since it can't prove, it can't verify it for itself, it has to trust that the someone is not abusing the trust. So it has to trust someone. That's why it's permissioned.
Uh-huh.
And this is the case.
Yeah, go ahead.
Sorry. Oh, well, just there is trust in every cross-chain system. By nature, what we're trying to do is get information from one place to another, where in the second place, you can't verify what happened in the first. So there is trust in every cross-chain system. And what we've done is try to minimize and localize that trust. Yeah.
Yeah, the idea of actually restricting specific watcher sets, like on the application layer, like on the application layer, that each application can choose their own set of watchers, is really, really cool. That's like a really brilliant idea, actually. Just in terms of managing, aren't these like sweeping decisions that everybody must opt into? It's actually it's a really cool idea. Just to see if I'm understanding right, is part of the reason why things need to be permissioned on the destination chain because otherwise people could kind of weaponize what's the word I'm looking for? Oh my gosh, challenges that they could just kind of needlessly challenge things in order to stop them up.
Exactly. Yeah. So what the watcher can do is basically just pause the channel, and they do that if they observe fraud and they need to do so to maintain safety. But because you cannot formally prove that or formally like verify that within the chain, there's trust inherent to the role. And so basically you want to have folks who are incentivized to maintain the safety of the application as well as the liveness of the application. So they're incentivized to prove fraud if it does happen and to not prove fraud if it doesn't. Or rather, attest to
Cool.
fraud.
I've also got a question coming in the chat. So the watcher from the sender chain can send fraud proofs, but on the receiving chain, they can only pause the channel by challenging them?
Correct.
Cool. All right. Awesome. And is there anything else that you'd want to point out before we hop into the code?
So I have like a question here. Apart from like the general bridging of like tokens, I suppose that's like one of the common optimistic bridges. But like, can you guys give an example of other use cases that you can do here?
Absolutely. I would love to. Yeah. So one small clarifying point in the intro is that NOMAD is not a bridge. NOMAD is a protocol for cross-chain communication. So at the core of what our protocol does, it's basically passing bytes arrays across chains. And those bytes can contain anything. And what's interesting about those bytes is that you can use them to program applications on top of this communication channel. So the NOMAD token bridge is one such application built on top of the NOMAD communication channel. And we have other applications built on top, as well as many more being developed in the moment. One we're really excited about right now is applications for cross-chain governance, and particularly at the moment, cross-chain proposal execution. So these are basically applications which allow DAOs that have a Governor Bravo contract on one chain and their protocol on another to pass proposals as normal on their governance contracts, but then execute them on remote chains. And this is a core application that we built into the NOMAD system. Our application has been governed by cross-chain governance for since day zero that it's been on mainnet. And so this is a really, really interesting application to us right now. And there are many more that I could note.
Yeah, that's awesome. That's super interesting that you can like just to think of the possibilities if you can send sort of generalized data back and forth across chains. One that like comes to mind that I've like wondered before is staking rewards, or yeah, I suppose if you have like a token and you have stakers, you before you, I guess you would need to have them all staking on one chain to work out who gets what share of the pool. But now potentially you could have staking rewards across multiple chains, and then have like fees generated across multiple chains and shared across all chains with all stakers.
That's right. Yeah. If I had to do a super quick rundown of like the application space, like we definitely know for sure that that the following things kind of work and are interesting. There's token bridges, like mint burn token bridges, and that can be for ERC20s or NFTs. There's multi-chain tokens. Again, that could be ERC20s or NFTs. There are liquidity networks, cross-chain liquidity networks, such as Connext, for example, which is built on top of NOMAD. And then there's governance proposal execution. And Superfluid has actually just launched an MVP of their sort of cross-chain asset streaming as well. There's a couple other applications that I think will be really interesting to us, but that we don't have the design space sort of as an industry necessarily figured out yet. I think cross-chain voting, like not proposal execution, but voting, will be really interesting. Staking, lending, and potentially oracles. Just a couple of applications that I'd be interested to see explored.
Yeah, really cool. Like when you started talking about how like the messaging protocol, so I was thinking of kind of like there does seem to be a big research goal that in the DeFi space in general of how to kind of pool liquidity from multiple chains together. And yeah, I was happy to hear you touch on that also, just to see that is kind of perhaps a potential direction somewhere in the future. Uh, One thing that I'd meant to ask, but I realized that I hadn't also, was what actually moves the messages between chains? So we have an attestation on a root or source chain, and then it's getting put somehow. It might be the easiest word for it, but I don't think it's actually the technical term on a destination chain. How is that message actually being moved from point A to point B? It might be easier if I give like an example of a way that it's not working. Polygon, for instance, with their bridge between main and Polygon's chain. So they actually just have baked into the client that the client listens for certain events, and then submits a transaction to the right destination on the target chain. Over here, is there something kind of like a client that's listening for certain events? Like how does the information get from point A to point B?
So basically, we have 4 off-chain agents, as you see in the diagram, right? We have the watcher, the updater, the relayer, and processor. All these are off-chain agents, programs. And basically, we don't pass the message per se. What the system passes is a root of a Merkle tree that includes all the messages that have ever been sent by a chain, right? So by the system makes sure that this route will find its way from Ethereum, for example, to Moonbeam, right? Now that if Moonbeam has this route, anyone can go to Moonbeam and prove that the message was sent from Ethereum because it's included into that route, right?
Mm-hmm.
And then the system will process that message because it's been proved that it exists in that route. So how the route goes from one domain to another. Basically, when you send messages, for example, from Ethereum, they go into a queue, and at some point, the updater, which is a trusted agent, it's the validator in other bridges or systems, which is bonded, will flush the queue and update the tree with all the messages that were into the queue and generate a new route. And we'll commit that route to the home smart contract, as we say. Okay, so now the Ethereum sending chain has a new route. The relayer, which is a trustless agent, anyone can do that role. Um, it's not bonded or anything. Uh, Observes that fact through, of course, events that there is a new route and takes that route from Ethereum and submits it to any other domain. Let's say Moonbeam. It goes to Moonbeam and say, "Hey, I have a new route. Here it is." And now the optimistic window starts. And in that optimistic window, the watcher can come in and say, "That's fraud. There is no fraud. That's not true. Uh, that's not true route. Maybe the updater or the relay, maybe the updater signed an incorrect route, or maybe the relayer submitted an incorrect route, or whatever."
I take it
If
that's
that
why it's
doesn't happen,
2.5.
Just
Oh,
a quick
yeah.
note. Just that the relayer can't submit an incorrect route, just because what is performed on the receiving chain is that the updater's signature is verified. So
right.
for any route to be relayed, the updater has to sign it. If fraud occurred, it is because the updater has signed an incorrect route.
Yeah, that's true. That's true. Otherwise, it would be very easy to do DOS. Yeah. Yeah. So we have that, and after the optimistic window passes, like the system accepts that that's probably the correct route, and the processor, which is another trustless role, basically goes through all the messages that has been observed in Ethereum through events, and goes through every message and proves it. Not every message, but all the messages that were meant to Moonbeam, and proves these messages under the route that's now committed in Moonbeam. Right. And now the messages were proved. They're not processed, which means they go to their final destination and execute whatever they have to be executed. And that's the end of the life cycle of a message. And then if Moonbeam wants to send to Polygon, it starts again the same process.
Mhm. Cool. I take it the reason why Watcher is labeled as like a 2.5 as opposed to like a rounded integer is because it's kind of like in the expected scenario, they don't necessarily submit a process. Everything is legit. So
Exactly.
there's no okay, cool.
Yeah, it's 1, 2, maybe a Watcher, maybe not. If not, then 3, 4, blah blah. Yeah.
Cool. So I'd say let's dive into some code, if you don't mind. We occasionally look at the Solidity also. So taking a look at the GitHub, it's kind of big. Probably going to need a little bit of guidance on what you think we should be focusing in on. Like I take it we should probably go to the contracts in the mono repo. Is that correct?
Mhm. I think we should maybe just do a dive through the home and replica to talk about the life cycle of a message. Basically,
Okay.
exactly this diagram Odie has just talked about. Contracts core. We do have a lot of code. Contracts. Home would be the beginning of the message life cycle.
Okay, sweet. So I've got that here, and then
Replica
Does it
would be
go-
the other
all right,
sort of relevant contract.
cool.
And if you don't mind, just like bumping up the code size, if you don't mind.
Yeah,
Ben.
sure. Cool. Is that good?
Yeah, awesome.
Right.
So let's start at the sort of dispatch message. This is the entry point for a message in the NOMAD system.
Okay, so here is dispatch of the event, but then you're talking about a function here.
You can grok for function dispatch. There we are. Awesome. Yeah, so as you can see from the message signature, or function signature rather, this is like a pretty simple concept here. So Dispatch is dispatching a message, sending a message through the NOMAD system. This message is that sort of arbitrary chunk of bytes that we talked about. And all you do to send a message is you call this function, you specify the destination domain, that's like a chain, domain, the recipient, and the bytes message body. So basically just here's my message and here's the address for it. It's kind of interesting in a cross-chain world, an address is no longer a unique identifier. So we talk about an identifier in the cross-chain world as this tuple of the domain or the chain kind of ID and the address. Something interesting you might note here is that the address is bytes 32 instead of like an EVM address. Reason for that is actually kind of cool. In the EVM, an address is represented with 20 bytes of data. But actually in many other VMs and most other chains, it's actually a 32 byte identifier. And we built NOMAD from day zero to be interoperable with different VMs. So right now we are only deployed on EVM chains, and we have a lot on our hands working on that right now. But we also have a system that can be extended pretty seamlessly to other VMs, and it is something that we are working on.
Wow, that's really cool. Yeah, I've noticed in other applications, people are using bytes 32 to represent an address, and then they just sort of strip off or add on a bunch of zeros to represent those, to kind of compress it down to the 20 bytes for the actual address. But that's like super foresightful that you guys have built this out to accommodate like non-EVM VMs.
Yeah, part of that is just that our team, members of our team, have been working in the cross-chain space for 4 going on 5 years now. They've been building cross-chain systems for years. So they've run into all of these kind of little things and, baked them into our system and that knowledge and experience. So we can go into the function body. It's actually it's pretty simple. So here's what happens. So, right, we get a nonce for the message, we get a little bit of metadata. The metadata for the message is like the local domain, that's the chain that the message is being sent from, the sender, the message sender, the nonce, and then of course the destination and recipient and the message body. We basically pack all of that information together into one big chunk of bytes, and we hash it. And then we insert that hash as a leaf in a Merkle root, a Merkle tree rather, sorry. So when we hash all this information, insert it into the Merkle tree, and that updates the root of the tree. Then we emit this dispatch event, which is a way for off-chain actors to observe exactly what message has been sent and what information has been hashed inside of that message. And done, voila. The end result of this is that a summary of this information has now been included inside of the Merkle tree stored in this contract. We can move on to the next step if y'all don't have any questions here.
Yeah, that'd be great.
Cool.
Yep.
So, right. So this is how an individual message is dispatched through the system. And you can imagine that this is going on all the time. We have applications built on top of the message passing channel that are calling this function to dispatch arrays of bytes. It doesn't really matter how many messages have been included in the root, just that at least one has been sent since the last update, such that we now have a new root of the tree. And that root is, of course, like basically the summary of all the messages. So the next step here is the update function. If you can grok for function update. Oh, or just scroll right down. This is where the first off-chain actor comes in, and this is the updater. If you have in your head mental models for other optimistic systems, such as, for example, optimism, you could think of the updater as like the sequencer. Basically, they're the single party that in the optimistic system attests to changes of state or information, and they have a bonded stake. They create these attestations, which can then be relayed. So the update is the place where this off-chain actor can submit an attestation to a Merkle root. And what they submit here is sort of bytes32 committed root. That's the last root that was updated. New root, that's the updated root, and just their signature. And this is literally just creating an attestation of a root. On the home, we can check natively if this attestation is correct, because the canonical information is on this chain. If it is, we just slash the updater immediately. But there's no reason why they would, submit a fraudulent update to the home. And then we update the committed root and emit an event. We actually are working on an upgrade here that's actually going to simplify this function. So we, have sort of over time realized that we can actually move to a slightly different construction where we don't even have to attest to the committed root. We can just create attestations to any updated root. And that will actually cut down some of the code in this function. Basically, yeah. So, but for now, this is mental model is off-chain actor submits an attestation to the data.
I think the one thing that I'm still catching up on, it could be I need to like deep dive back into Merkle trees a bit more. It's been a bit for me. The while loop over there, which you were just talking about. So what needs to get DQ'd doesn't? Like I get the feeling it's not taking out all of the previous leaves and putting in all of the new ones. It's like only certain things need to be removed.
Yeah, so this is a piece of code that we're going to deprecate. But the way it works right now is part of the like fraud proof system is that when new roots are enqueued, when new messages are dispatched, those roots are added to a queue. And then when the update is submitted, all of the interim roots are dequeued. And kind of the purpose for this, yeah. The purpose for this is kind of being able to prove that this root was a valid, this root existed, like this was a valid root.
So I mean, basically, if I'm understanding right, which I'm totally not sure that I am, so like Alice calls dispatch, that gets put in the queue. Bob calls dispatch, that gets put in the queue. Carol calls dispatch, it gets put in the queue. Once we hit update, we're only going to be putting in Carol's root. So what we need to dequeue is we need to dequeue the roots that Alice and Bob created, kind of stepping up to Carol's root, which contains all of that, like all of their, also the additional leaves that got added by Carol. Is that right?
That is correct. That is correct.
Oh, phew. I was okay. I had low confidence I was going to get that right. Okay, cool.
No. You were exactly right. For what it's worth, I don't like this code. We're gonna get rid of it. But yeah.
And so wait, and how would the new code work? The new code would work that. Yeah, actually, I don't remember. How did you say the new code would work?
Yeah. So actually, basically what this upgrade is going to do is it's actually going to simplify the process of creating updates as well as proving fraud. And so it will deprecate the use of the queue entirely, and actually just store interim roots. We're still in the design phase for this, so I don't want to like I don't want to yeet my opinions publicly. But
I'm reminded
the
of
way
when
this
like
works.
the game demos it says like footage captured from like pre-release alpha subject to change
Yeah.
kind of stuff.
Yeah, James is gonna kill me. I'm like, here's how this is how we're gonna write the code. He's like, oh my god. But yeah, so anyway, basically the way that it's going to work is it's going to remove the concept of like right now we're committing to the last updated route and the new route. So each of these updates creates a chain from like the 0th update to the latest one. But we don't actually need to do that. We can just attest to a single route, the latest route or an updated route. There's no need actually to create this chain between like the old route and the new route. And that's going to like simplify this flow.
Cool. Very cool.
So the next step in the process is a jump from the home to the replica. And this is where the second off-chain actor comes in. So the updater has created this attestation to a new route. They have submitted their signature on chain that this route is valid. This is when the updater is a permission role, as you know, they're bonded on chain. And then the relayer is our first sort of permissionless actor. So because this updater has signed the route, their signature is easily verifiable on any other chain. Anybody can come play this role of a relayer and just take their signature from the home chain and submit it to the receiving chain. So that function is called update also on the replica. Yeah. Function update.
Oh, yeah, so update also, but yeah, update.
And as you can see, it's exactly the same function signature as kind of the update function on the home. It's just old root, new root signature. And what happens on the replica here is you just basically check, is this the updater signature? Yes. Okay, cool. Let's set the timeout for this new route and let's update the committed route. That's a piece that's going to be deprecated as I discussed, but basically, cool, we got a new route. Let's set this timeout for the new route. As long as the updater has signed this new route, we accept it and we put it under a time lock.
I think you answered this already, but I missed it. How the updaters are on the replica chain? Or in other words, what stops me from kind of just maliciously signing arbitrary transactions that I feel like and just submitting them on the replica?
Mm-hmm. Well, that's exactly the core of the optimistic system, is that it's possible to do that. The updater can do that. This is built into the system design. The idea
Okay.
is that, right, yes, the updater can commit fraud, but there's two reasons why they wouldn't. First, they will certainly get slashed. Second, they will very, very likely get blocked from any malicious thing they were trying to do in the first place. So they will get no benefit and certain detriment.
Got it.
The concept here being that, in these systems where we do need to create an attestation, we can simplify and reduce overhead down to just a single party creating that attestation. As long as the incentives are such that it's highly disincentivized for that actor to basically try anything.
Yeah, very cool.
Yeah. Great. So we have this sort of we have this new route. It's under a time lock. It's been submitted to the replica, and it's a summary of all of the messages that have been dispatched. Now, off chain, we wait for this time lock to tick down. This is the time period during which, if there's any funky stuff, if there's any fraud, if there's any malicious messages inserted into the route, this is very easy actually for off-chain actors to see, the watcher, that is. And this is the time period during which they have the opportunity to block any fraudulent route. But let's assume that the time lock ticks down happily, and the route is now, past the time lock. Now we jump back into individual messages. So, right, dispatch is for a single message. Update is for a summary of message on home and replica. And then now we have to process individual messages. So you can go down, proven process calls prove, then calls process. Prove is a function where we submit a Merkle proof that this message is included in the Merkle route. So if you grok function prove, yeah, there we are. Cool. So what we know, quote unquote, on chain at this point is the route, like the summary of the messages. And so somebody off chain has to supply the actual original message. And so what we do in prove is they come in and supply the leaf, that's that hashed summary of the data, and a proof that that leaf is included in a route that has timed out now. So that's what you're seeing here, is it just calculates the Merkle proof. If that proof is for a valid route, then this leaf can now be considered proven. And then we can move on to the process stage. And this is when a message actually takes effect on the receiving chain. So I think it's maybe just above this. Yeah, there we go. So this message, it's valid, right? We know this at this point. It's been proven to be included in a route. And so what we do here is just pass in the full message, hash it, check that it is proven. And then, since we know that it's proven, call into the application with the contents of that message, and then mark that message as processed. So what you're seeing here in this handle function is exactly that. It's calling into the application and passing this message. So applications on the sending side call into the home to send messages, and applications on the receiving side are called by the replica to receive messages.
Okay, awesome. Yeah, that makes sense. Sorry. Yeah, it's like 4 a.m. where I am right now, so I'm just trying to keep it down a bit. No, that's awesome. That makes sense. So then in this handle function, is there anything interesting going on there? Or was that just sort of calling with passing in a bunch of data?
That's where everything interesting happens.
Yeah.
So what we've gone through just now is a system for passing arrays of bytes across chains. And, we just walked through, we have a solid understanding of how these arrays of bytes, doesn't matter what's in them, we're schlepping them across chains. That's the core of what NOMAD is. But why that matters, why anyone should give a damn about that, is because you can program applications on top of this. So all of the interesting stuff really about this system, everything that it actually does for end users, happens at the application layer, at the layer that actually calls dispatch and receives handle functions. And we can go through an application if we have time, or if y'all are interested.
Sure.
I'm all for it personally.
Yeah.
Yeah. I'd be really interested.
Great. Let's do.
It's worth.
Go for it.
I think, Anna, it's worth mentioning to typed memview. Like, it's a library we use. If you notice the bytes 29, it's a very weird data structure. Like, who used bytes 29, right? So we have like an in-house library that was, I think, was made by James like a while ago, and basically makes all of this very efficient. So all of this functionality you see, it's very efficient with a very surgery-like functionality on
Precision.
bytes. Yeah, exactly. Precision on bytes in the stack with no excessive copying or cloning or anything. So it's worth mentioning that if anyone wants to dive into, they can search for the library typed memview. They can find it in the source, and it's very interesting. It's probably the
That is
most
really cool.
efficient way to handle bytes arrays. It's probably the most efficient way there is, and not go into raw assembly.
Once we are talking about efficiency, I was like telling myself I'm not going to say anything. I'm not going to say anything. But it was interesting to me that you guys used 1 and 0 in the reentrancy guard. There is like a famous little piece of gas optimization to use 2 and 1 instead of 1 and 0. But very, very, very minor though.
Flamed.
But that is, huh?
I said we just got flamed.
No, it's like I'm not like such a optimizing, like, whatever. And especially once you're comparing to something like how you're parsing, how you're encoding, and how it's going to be like, I mean, there's going to be a very, very low ceiling, I think, on exactly how much extra gas it is. 100 gas, maybe? I don't remember off the top of my head. It has to do with once the slots. What is it? Do you remember the specific details on warm slots 1 to 0?
Yeah. When you initialize, it's the same, I think, with dust, right? I think that's the same thing.
Yeah, exactly.
Yeah, it's so expensive to set a slot from 0 to something than it is to set it from something to something else.
Is that only starting 0 though? So maybe you get around it because you're
That's
starting
exactly
as 1
right.
and going to 0 and going back.
That's
so you get
exactly
the optimization.
right.
I was even wrong.
Indeed.
Excellent.
Indeed, yeah.
All right.
Yeah, so we start, exactly. So when we set it from 0 to 1 at the end of the function, that slot is already warmed, so we don't have to,
Very cool.
So
interesting. I didn't realize that.
Yeah.
All right. Well, I learned something new.
We first flamed, William.
Indeed. Yeah. I definitely do want to see the encoding decoding library.
Yeah.
But I think for now, probably seeing an application. What do you think, Ben? Think going for an application probably makes sense?
Yeah, I'm keen to see an application and how it handles.
Yeah, I think we should, let's do that because it kind of ties together what matters about this. Let's go to the governance router. So in contracts core, contracts, governance router. Here we are. Cool. So basically, as I talked about, right, we're sending bytes across chains. Why does that matter? We program with that. So let's talk about the message lifecycle from the perspective of an app. An application can treat this whole system, can treat NOMAD like a black box. All it cares about is sending and receiving messages. And something to call out here is that we have basically talked about this design of like a router pattern. That's the naming that we have sort of chosen for this. But the idea being that these contracts are isomorphic. They implement this functionality for both sending and receiving messages. And this means that they are build once, deploy everywhere. The same code is deployed on every chain. There's one router on every chain, and each router handles the functionality of sending messages to its fellow routers, to its fellow instances of the same application, and then receiving messages from its fellow routers or its fellow instances of the same application. Let's start with the actually dispatching. So let me scroll down a little bit. Here, execute governance actions.
Sorry, I was muted. Yeah.
Cool. So this is the concept of the governance router is kind of similar to like it's basically a place where permissions for the protocol are aggregated. So anything governable is owned by this contract on any given chain. any governable functions that can only be called by a permissioned role on the protocol layer, are all those permissions are aggregated to this contract. And so the point of this contract is just being able to call those functions, and to have one owner that is able to initiate calling those functions. So this application is kind of interesting. The bridge application that we have, the token bridge, they're all, each instance of the router is sort of equal to each other. Every bridge router stands on equal footing. But the governance router is different because there's a hierarchy. There's like a hegemony of these routers. There's one router that is on what we call the governor chain. In our case, it's Ethereum. And that is the router that is able to send messages to everyone else, or to every other router, every other chain. And then, right, the other routers are sort of just there for receiving the messages. So even though they all implement the same functionality, messages only flow from one router to others. Part of what's interesting about that is that you can actually transfer ownership across chains, and these contracts will work like out of the box the same. So if there's no questions on that, I can just jump into what you're seeing here. It's basically it's pretty simple. You see this modifier, only governor or recovery manager. The governor is kind of the quote unquote owner of this contract. And that's basically like plug and play for governance consensus, be it as it is right now, a multi-sig as we're sort of bootstrapping this protocol, or be it something that has more like on-chain or sort of more complex rules for deciding how to submit governance actions. There is an owner for this contract, and when this contract is tasked with executing proposals. So you pass in the call data, like you pass in the information of calls. There are calls to the local chain, which are executed immediately, as you can see in this call local loop on line 269. So every call for this chain gets executed instantly. And then we go into this call remote loop, where we have an array of remote domains, other chains, and an array of calls. And for each remote chain, we send those calls. So if you go into call remote, this is where we interact with the NOMAD protocol for kind of the first time, like the underlying message passing channel. And all that it's doing here is it's got a domain, and it gets the address of the router for that domain. It formats these calls into a message, and then it sends that message. So it's pretty simple.
Okay, interesting. So I saw, just going back a step, I don't know, yeah, right here. So we're passing in specifically the local calls, and then the remote calls, but these are paired with the domains, right? Because these have to sort of identify the chain ID for each remote call. All right, yeah, that makes sense.
So these transactions, these calls will be passed to the router on the destination chain, and then executed from that router. So that router will have all the permissions on the protocol, and if we want to call any of those functions, then we basically send these calls across to that other router to be executed.
Interesting. I wonder if is there any sort of like problem with calls becoming circular? So like a chain, so let's say Ethereum mainnet calls Polygon, and then Polygon calls back to mainnet, which calls back to Polygon. Is there any problem with that?
So we talked a little bit about the sort of hierarchy between these routers. This is different from the token bridge, but in the case of the governance router, there's only one router that is allowed to call other routers. It's the governor router. So the router on Ethereum calls every other router, the router on Polygon, Arbitrum, Optimism, etc. And it can't go the other way in this case.
That makes sense.
Yeah. The reason for that is because we actually have to have like consensus for what governance actions to execute. And we don't want to achieve consensus between like disparate chains. So the way we've done this is like, okay, cool. Or rather, if we achieve consensus between different chains, like that has to be settled on at least one chain. On only one chain. So one chain is responsible for the settlement of governance transactions, and that is the chain that can call every other chain.
Gotcha. Yeah, that makes sense.
This is part of, we talked a little bit about applications that haven't been sort of super figured out yet, like voting. This application achieves proposal execution very successfully. We've been using this in production to enroll new chains since we deployed. So this is like a fully functional proposal execution protocol for cross-chain governance. But in terms of like right now, it treats settlement of governance decisions like a black box. And right now, that is just simply a multi-sig of like members of the sort of cross-chain community. But in the future, you can imagine that process would be a little bit more complex. And the question of voting in a cross-chain environment is one that just hasn't been solved yet in a very adequate way. So it may well be something that we're looking to solve at some point.
I mean, this at least gets a bunch of the way. It was a problem before, like when you have governance living on one chain, but like especially if it was Ethereum's mainnet, and then with gas costs, it just gets untenable to like keep on doing the same operations on the same chain. Was the way to like have governance on chain A affect something on chain B, and this at least, I mean, this does get that far. So even in terms of like improving the execution from there. Like, I mean, this is still a major step.
Mm-hmm. Yep. We thought it made sense to break up the problems that we're tackling here. And execution, we know we can do, and we've done it, and we're using it, and it's great. And so we move on to the next step in the future. But anyway, back to the application lifecycle. So we've just called dispatch on the home. That function which sends a message through NOMAD. And what that's done is it has sent these calls across to a new chain. So let's go up to function handle.
Function handle. There we go.
Yep. So this is being called by the replica in the step process. At the end of that message lifecycle, it calls into the application. This is some typed men view stuff here. It's sort of like checking into this bytes array to check information about it. Namely, we include like identifiers for what type of message this is. In almost all of the cases, it's going to be like a batch. That's what we call like a batch of calls. So you can sort of go into handle batch.
Handle batch. There we go.
Cool. So something I didn't super touch on was that instead of actually passing all of these calls across chain, what we do is we hash the calls and we pass the hash across chains. So it's a much tighter piece of data to be passing across chains in this case. So all that happens in handle batch is that we get the hash from the message. and we store it on chain, and we emit an event. And then if you scroll down one, we have this message execute. So once a batch has been stored on chain, you can pass in the original calls and execute them on chain. So here we pass in the calls. That's the original calls that the governance router had sent. We hash them and we check that that hash has been stored. And then we loop through each call and execute them. And then
That's
like,
really cool.
voila.
Yeah,
Nice.
that's really cool.
It's elegant.
Yeah. Agreed. So excuse me, we're running up against time. So are you guys gonna call it here? Like, this seems like a pretty decent kind of stopping place. It gives us like a pretty good view into what building an application on top of NOMAD looks like. If there is anything else that you want to end with, like, I know personally I'm fine schedule wise. We could still go like for a few more minutes if there's anything you want to wrap up with or anything like that.
I mean, I definitely have things that we could chat about. I think this is like a very nice stopping place, but I would love to keep talking, but yeah.
Maybe we could do two.
I mean, do
if
another app?
you guys are interested in a sequel, but maybe just like a reschedule, like do a second episode in the future. I would
Oh,
be
yeah.
very interested in it personally.
Yeah, I'd be keen
Let's
to
do
do
it.
an episode 2.
Okay, awesome.
Yeah.
All right, so we'll try. So while we stop here for now, then,
All right.
and yeah, awesome. So Odysseas, Anna, thanks a bunch. I really think this has been one of the clearest like presentations that we've had since we've started. Like taking a complex protocol that's handling really a complex activity, moving things between chains. Able, like, first of all, just to present it this well, but also even inside the code, just the level of realism, I'd say, and the code, like, really, really awesome to see. So yeah, we'll try and work out another one of these. And in the meantime, yeah, this is Solidity Fridays signing off for the weekend.